Hi everyone, my name is Duarte and I'm a machine learning engineer here at Lotus Labs, and I'm here to teach you everything you need to know about RAGs, Retrieval-Augmented Generation, what it is, why it is used, and I really want you to have an intuitive sense if you should be using RAGs for your generative AI application. If you're interested in more AI tutorials, generative AI tutorials, or videos about diverse topics in this field, please don't forget to click the like and subscribe button below, and we will see you in a bit. If you are watching this tutorial, and you probably already know what an LLM is, right? But even so, I want to explain from a point of view of RAGs, why were RAGs created and what problems are RAGs trying to solve. What is an LLM exactly? When training an LLM, you take a huge slice of the entire world knowledge. So basically the whole entire public internet, more books and documents that anyone could ever read in their entire lifetime, and use all of this data to train these LLMs. Okay. To give you a more direct comparison, Llama 3.1 was released in July 2023 and was trained on a corpus size of 15 trillion tokens. And this is about 112 million books if each of these books would have 400 pages on average. And so if someone would go and have this tremendous task of attempting to read by itself all this textual data that Llama 3.1 was trained on, at the regular human reading speed, it would take round about 145,000 years of continuous reading to read one pass through all of this textual information. And this is to give you a sense on how large is the textual data that these models are actually trained on. And what happens in this training process is that all of the knowledge and concepts and theories and events that happen on the world that are represented in this textual data, they get represented and stored in the model weights of these LLMs. And when you're talking with them, you are in a sense querying this entire public knowledge, which is a pretty cool outstanding feature of talking with an LLM. You're basically querying this vast amount of publicly available information. Another thing to consider is that the rationale behind the algorithm of these models looks pretty naive and frail and looks like it wouldn't work. Okay. But it works. What these LLMs are basically doing is that they, given a string of text, so an array of text, they are constantly predicting the next word in a sequence. They are basically very highly sophisticated and powerful auto-completing machines. They have a beginning of the sentence, and they predict the next token. Let's simplify to the next word in the sequence. Then they feed that recursively and then predict the next one, and then the following one, and then the following one, and then they use that to answer to your question. Okay. And they have also been, because of this, called stochastic parrots, because they are just, in a sense, parroting what they have learned in this huge corpus of textual information. And based on those linguistic patterns that they learn in this huge corpus of text, they are predicting a probability distribution of the most likely next word in this sequence. Okay, so when you have a very powerful mechanism like this, and you have this very naive and simplistic methodology of constructing a conversation, you obviously have some drawbacks and some pitfalls in the LLM output. So there are three main problems with LLMs that RAGs attempt to solve. Although LLMs were trained on an absolutely massive amount of data, they do not know everything. Okay, first. They were trained with data up until a particular period of time, and they do not know anything after that. LLMs on their own cannot retrieve any new information post-training. And since what LLMs are continuously doing is finding the best next word in a sequence of text, you can immediately see where that might go wrong in some cases. First, they have a bias towards providing an answer, even if that answer is incorrect, right? So think of this. LLMs inherently attempt to generate coherent, confident sounding answers rather than expressing uncertainty or withholding judgment, since this is what the training data mostly looks like. There isn't typically a lot of doubt in the internet or in research papers or in books. If someone is writing about a topic, then they typically are writing because they know what they are talking about. And LLMs, as the parrots that they are, often mimic that confidence even if they don't know what they are talking about. Okay, they do not really know what doubt is. They don't have a world model. They just learn everything from this textual information. They do not feel uncertainty or doubt. They are simply finding the next most likely word in a sequence based on all the training data. So there is this phenomena, and this phenomena that is highly studied in LLMs, it's called hallucinations. They hallucinate and generate information that looks very plausible, and they are very good at responding with very plausible information, but it's sometimes actually incorrect. And the third point that I want to mention is that LLMs have a limited context window size. Basically, when you're interacting with these LLMs, they only process a maximum fixed size of number of words or tokens. And this varies from model to model. So what happens if you have an extensive conversation with these LLMs and then you ask them what was the first question, then they might not know because the entire conversation you are passing to the LLM was already past that context length, so it gets truncated. Okay, so basically you're not providing the full conversation to the model anymore, so they have no idea what you said at the beginning of the conversation. Let me go even a little bit more in detail about this context length. There is this very important test, which is the needle in a haystack. You basically place a needle or a piece of random information that is not even related to the underlying text, and you hid that information somewhere in the prompt in different places. Okay, and you send several prompts with different sizes. Okay, so on the x-axis you have the size of the prompt, and on the y-axis you have where did you place that information. Did you place at the beginning of the prompt, or you place in the middle, or at the end? And you construct this heat map. Okay, and then you test the ability of the LLMs to retrieve this needle, retrieve this information. So this needle in a haystack test is going to evaluate the model's capacity of fact retrieval. And for ChatGPT 4, it will forget more at the beginning of the prompt, and we also see that it forgets slightly more at the end of the prompt. If you have a very big prompt, it will tend to forget more, or it will not be able to retrieve as much facts from the beginning of the prompt, and also slightly worse at the end of the prompt, which is pretty interesting. It remembers more the middle part and less at the beginning and less at the end, but much lesser at the beginning, as the image suggests. And this changes from model to model. Not all models behave and have this test presented in a similar manner. I would like to show you the needle in a haystack problem for Gemini Pro, which is very interesting indeed. So this is not a typical model behavior whatsoever. For some reason in this test, it was very bad from the 3.2 to 5.4K tokens context length, but it did a decent job afterwards. Notice that this is not the same scale as the previous image that I showed, but even so, this can be useful for you to also have understand that each model has its own context window blueprint in a sense, and you could use this. If you know your model, you can use this to be a better prompt engineer and do better prompt engineering. And the idea of RAGs is, wouldn't it be nice if we could prompt the model to have its prompt be in the boundaries that are best for the model to retrieve the information? So all of these three problems can be largely solved through RAGs. What exactly is a RAG? RAG stands for Retrieval-Augmented Generation, and it's an AI framework that combines retrieval with text generation and allows models to pull in external knowledge to improve responses. So you have a large documentation or information about something that is not publicly available, This documentation is something that you create for this purpose or even already exists, and you want to pass this documentation to the model so it can answer to user questions, for example. So when you pass this documentation to the model, it will have extra knowledge available. And not only that, what the RAG allows you to do is that it will only provide the necessary information and the relevant information to the model to answer to that particular user question. So if a person asks something related to the purchasing department, then it will only provide information to the model. The RAG will only provide information to the model relevant to answer things about the purchasing department, for example. So you can construct a huge RAG if the user question has nothing to do what is contained with what is contained in the RAG, or if what is contained in the RAG is just one or two sentences. In an optimal scenario, what you want is that only that information that is relevant is passed to the model and not the full documentation. Okay. So using RAGs is also about model efficiency and cost efficiency. Instead of sending a huge prompt each time to the model, you are really just sending important information for the model to respond to the user question. Besides, your input size to the model will also be lowering costs significantly. Okay, and as we saw before in the heat map with the needle in a haystack problem, there are certain if the context that you're passing to the model is too large, it will have more problems with fact retrieval. Therefore, when you use RAGs, you are also limiting that problem because you're setting the context size to a certain length. In a sense, you're just passing a certain number of chunks from your documentation to the model, and therefore you're more limiting and you're making sure that that prompt has a more contained size. So basically, you are going to be located more in these regions, and that's what you're hoping for, that you're going to be contained more in these regions, and the model will be able to therefore process that information more effectively. Okay. So how does the RAG framework work? So imagine you have all of this documentation you want to provide to your model, and then you have this documentation, and these documents will be split into chunks. And you can split this chunk size, okay, the chunk size. And these chunk splitting RAG tools not only will split into chunks, but will also often guarantee that you don't split these chunks in the middle of a sentence. And this chunk splitter generally also will look at the semantic meaning of the documents and aim to keep these chunks in the size that you specified on, but also keep these chunks as independent between each other as possible. And yeah, the goal of this chunk splitter is not only to split or more or less on the size that you asked for, but also to create these self-contained chunks that retain enough context to be useful to answer to the user question without relying heavily on adjacent chunks, on another chunk. So this is what the text splitter does. Okay, the chunk splitting RAG tools does. After you choose a chunk size, and this will vary from problem that you're trying to solve from problem that you're trying to solve, okay, and it depends on the documentation that you're passing on. You also have to fit the chunk overlap. So to make sure that the model understands and mitigates this problem of having separate chunks of information, the chunk overlap is a parameter that will overlap. Each chunk will be overlapping with the next chunk. Okay, and yeah, so based on this, it will construct all of the chunks. So you provide a huge amount of documentation. This documentation is split into chunks that you choose more or less the size, and you can see how these chunks are being split with open source tools. And then you pass these chunks to an embedding model, and the model, what will do is transform these chunks into vectors, and it will embed. This is the process. This process is called embedding, and it will store these chunks in a vector database. Okay, and these vectors have semantic meaning. Each chunk has its own semantic representation, its own semantic meaning. And this semantic meaning is represented by vectors that point to a location in a very high dimensional vector space. And this comes back from how the attention mechanism works and how these models perceive contextual and semantic information. A classic example is if we think ourselves, if we think as the word queen, we immediately see a picture of a queen, probably wearing a crown or something like that. But if we, before a queen, say the band Queen, then we think of probably Freddie Mercury or something like that, right? So each of us has their own embeddings, in a sense, their embeddings in their mind. And each word that we are associating, we associate it with an idea. And that's exactly what these vectors attempt to. They have several dimensions, and each of these embeddings points to a certain dimension. And if that word is accompanied with different words in that sentence, these vectors will shift direction, and those directions will cause the meanings of these words in the sentence. So these meanings are all stored in a vector store. Okay, so it's a database, a vector database. And the things that you can do now is that when the user asks a question, you can see from this question, is this question related more with which chunks? Okay, so we have all of these chunks that were splitted, and this question from the user is more related to which chunks. So we kind of rank these chunks in terms of similarity from the in comparison to the user question, and we are going to pick the chunks that are more similar to the user question, and we are going to provide those to the model. And therefore, the model will only receive these chunks that are very similar to the user question, in hopes that it will look for these chunks keyword based or semantic based, and it will provide only these relevant chunks to the model to answer that question. So the model, what will receive is the user question, all the documentation that was fetched from the vector store, okay? So all of this documentation that comes from the vector database, and all of this added together, concatenated, this is what goes inside the LLM. And as I mentioned before, hopefully this is much shorter than just feeding the full documentation to the model, and it turns out it's also much faster and much cheaper. Okay, so yeah, finally the LLM answers to your question, and hopefully it answered correctly and it fetched the correct answer. So this video was intended to be a very lightweight, superficial video on RAGs, just to give you an intuitive sense on what RAGs are and why they work. And there are several types of RAGs, and we are planning on making a few videos on that and showing actual code on how to implement these and some tips for constructing RAGs more reliably. And even if you don't know yet all of the nuances, I hope you now have a pretty good overview picture and can have an intuitive sense if you should be using RAGs or not in your generative AI application. And just to let you know that we are planning on making more videos about other AI or machine learning topics. So if you found this video interesting, please click the like and the subscribe button, and we will see you next time. Bye. See you.